Okay, then let's start and kick off the new year, which will be awesome because 2020 was so bad, so 2021 is going to be awesome. Let's kick it off with statistics for data science. And as I announced before the Christmas break, we are now actually finally starting with some statistics after, of course, we reviewed a lot of probability theory in the first part of the course, and obviously statistics and any kind of uncertainty interested data analysis rests on probability theory, so that's essential to do that. But of course now it's also time to start thinking about statistics proper. And we start today with some general introductory remarks to statistics, and then the most popular method to derive point estimators in statistical models, namely maximum likelihood estimation. So this is all standard material. Here are some references, but you find this in all books that develop statistics with some math. The plan is to first talk about what statistical models actually are and what point estimators are, and maybe even more generally what aims of frequentist statistics are. Then to discuss maximum likelihood estimation and do that with a number of examples. Maybe one more remark on the general outline of the course. We are now starting with statistics, and we will for I think 4 or 5 weeks be concerned with frequentist statistics, which is of course in an applied setting the most common form of statistics used. In the end of the course, so the last 3 sessions are then also devoted to Bayesian statistics, which are also of course very sensible, but in the applied world not that popular for unknown reason, and it's a long battle between frequentist and Bayesian statistics, which from my point of view is a little bit over, but they are both there, both are sensible, and we will see Bayesian statistics later on today. And now kicking off statistics proper, we start with frequentist statistics. Okay, then let's just get started. So first, statistical models. Statistical models can be defined as sets of probability distributions, which of course immediately links statistics with probability theory. So we need to know what probability distributions are if we want to say anything about statistical models. And there are 2 main forms of statistical models, namely parametric and non-parametric statistical models. Parametric statistical models are statistical models that can be parameterized by a finite number of parameters. And non-parametric statistical models are statistical models that cannot be parameterized by finite number of parameters, so that have infinitely many parameters. And in this course we are only concerned with parametric statistical models. As I mentioned at one point, there is a course on non-parametric statistics offered by Charité in the data science spectrum. So if you're interested in non-parametric statistics, that's something that you might want to look into. Last year we did a lecture on non-parametric methods with things like kernel density estimation, histogram estimation, and that's fine, but it's I think to really develop non-parametric statistics, that's of course not enough, so I decided not to do any non-parametric statistics at this point. Yeah, and non-parametric statistics, of course, is not meaning that there are no parameters and everything is clear, but it means there are infinitely many parameters. So essentially, you have to estimate the probability for each and every outcome. So you don't, you only make the assumption that there are probability distributions, and hence, yeah, your constraints are of a different kind. So it's quite different from parametric statistics. Parametric statistics, of course, being in the general world, of course, very popular, and hence it's also useful to discuss them. Again, a statistical model is a set of probability distributions, and we are concerned with parametric statistical models, which are statistical models that can be parameterized by a finite number of parameters. Typical parametric statistical models then have this form. So our parametric statistical model here has this label P, and it's a set of probability mass or probability density functions over some observed data X, and it's parameterized by a parameter vector usually. So sometimes it's only one parameter value that you're interested in, but if you think of the Gaussian, you already have two parameters, the expectation parameter and the variance parameter. So usually the parameter is a vector, and these parameters are of course associated with their own parameter space, so there might be certain constraints of the values that the parameters can take on. Here are two examples. So we've already established what a random sample is. So we introduced this notation. So we have random variables x1 to xn, and then we have this tilde, which means distributed according to, and then it means that there is a distribution that has a PDF or PMF, in this case a PMF, which corresponds to the Bernoulli probability mass function, Bernoulli distribution probability mass function, and this distribution probability mass function has a parameter mu, and this mu has its associated parameter space. So the important thing here also to remember is that this notation, that you have a random sample, means that x1 to xn are independently and identically distributed. So each one of those random variables is distributed according to a Bernoulli distribution with the same parameter, and these random variables are independent. That's all in this notation by convention. Another example for a parametric statistical model would be this parametric statistical model. You have a random sample that is distributed according to a Gaussian distribution with probability density function P mu sigma square, and here the statistical models would be the set of all normal distributions or Gaussian distributions with parameters mu sigma square, which form the parameter vector of this statistical model, and take values in the Cartesian product of the real numbers and the positive real numbers. Yeah. So a parametric statistical model is just a set of distributions that can be parameterized with a finite number of parameters. A very common parametric statistical model that underlies most of the commonly known frequentist procedures like t-test, simple linear regression, multiple linear regression, ANOVA, ANCOVA, and all their variants, is the general linear model, which is commonly denoted like this. You have an n-dimensional random vector of observable data, which is constructed by the product of a non-random design matrix n times p-dimensional multiplied with a so-called beta parameter, which encodes the effect sizes of the independent variables that are encoded in the columns of the design matrix, plus some Gaussian error. this Gaussian error is centered on 0, and in the basic form of the GLM has a spherical covariance matrix, meaning that the covariance matrix is given by a scalar parameter sigma square multiplied with the n-dimensional identity matrix, and this whole thing corresponds to a probability, a multivariate Gaussian distribution over the data with expectation parameter centered on max beta and covariance matrix centered on sigma square covariance matrix sigma square in. So here the set of probability distributions are all these multivariate normal distributions with fixed design matrix and varying parameters beta and sigma square. And simple multiple linear regression, Theta, ANOVA, and ANCOVA are all special cases of the GLM. Obviously, this introduction to statistics is not a GLM course. You know that there's a GLM course that I'm teaching in the SCAN program, so if you're interested in more details of the GLM, yeah, have a look there. It would be good if there would be a GLM course in data science, but what can you do, especially if nobody at this university really supports this. Anyway, good. So that's the GLM. So these were like 3 examples for parametric statistical models, and the GLM, at least in the frequentist setting, being the most prominent one. However, it has many special cases that we will also look at, like t-test, for example, that one can also look at without the background of the GLM. Then the GLM is more like a mathematical unification of many things that we will also look at in this course. Now that we've seen parametric statistical models and 3 examples, we will now delve into these parametric statistical models from the perspective of frequentist inference. We will then later also look at parametric statistical models from the perspective of Bayesian inference, but as I said, we start with frequentist inference, and there are 3 standard problems in frequentist inference. Also in Bayesian inference, but there they look somewhat differently and they are addressed differently. So we focus on frequentist inference first, and here the problems are parameter estimation, confidence interval evaluation, and hypothesis testing. So parameter estimation is kind of the most basic of these problems, and the aim here is to find a best guess for the true but unknown parameter value of the model, typically based on the observation of some data. So the idea is that, and this will come up repeatedly, that in the world there is a true but unknown parameter value. Your statistical parametric model is the set of all distributions of a specific parametric form, and you're trying to, in point estimation, identify that parameter value that is in some way close to the true but unknown parameter value. Yeah, you will never know the true but unknown parameter value, so there's no way to identify what's actually going on, but you can guess it, and you can have estimates of the true but unknown parameter value. And then, of course, in frequentist statistics, as we will then develop in next week's and the week after that session, you can ask, if I assume that I know the true but unknown parameter value, how good are my point estimates, or how good are my statistics? And that's then studying the qualitative behavior of point estimates, and we will or point estimators, and we will see more about this. So the first fundamental problem is to identify the true but unknown, or try to estimate better because you will never be able to identify it, to estimate the true but unknown parameter value that gave rise to some observed data under the assumptions of a given model. The second problem of frequentist inference, which we will talk about 3 weeks from now, is confidence interval evaluation. Here the aim is to provide a quantitative uncertainty statement about a parameter estimate based on the parameter estimate of sampling distribution. So in a way you try, so you can view it like this: with a point estimate, with a point estimate, especially if you're talking about the real numbers, you will most definitely be wrong, because the probability that you are exactly right is 0. With a confidence interval, you increase your probability of being right, but your precision in your estimate goes down. So you are not saying, okay, I think that true but unknown parameter is 2.12, but you're saying it's somewhere around 2.12 with a certain bounds, so maybe between 1.9 and 2.3 or something like that, but there you can be more certain that it's actually there than you are with your point estimate. And how that exactly works, and what the interpretation of confidence intervals and estimates are, and how they differ from credible intervals, we will see in Bayesian inference. All this we will of course cover. And finally, there's hypothesis testing in frequentist inference, there you're trying to decide based on some observations in a sensible fashion whether the true but unknown parameter is in one of two mutually exclusive subsets of the parameter space. So there you are even more imprecise. You're not giving only an interval estimate that may or may not be quite large as well, but you just partitioning parameter space in two subsets, subset theta 0 and subset theta 1, and then you're trying, then you just say, okay, the true but unknown parameter is either in theta 0 and theta 1, and you give some error bounds on this. There's actually quite a close connection between confidence interval estimates and hypothesis testing estimates if you set the confidence intervals in a specific way, and this is also what we will cover. But from an intuitive viewpoint, you can view this hierarchy here as going from very precise estimates that are most definitely wrong to very imprecise estimates that are most likely right. Well, if you are very imprecise, then it's likely that you are right. If you say, well, the parameter is a number, then it's likely that you're right, but you're also fairly imprecise. If you say the parameter, true but unknown parameter, is pi, then you're most definitely wrong, but you're very precise. So that's the hierarchy here, and we will spend some time on point estimates and studying the analytic properties, but then also cover confidence and hypothesis testing afterwards. Maybe that's one thing that one can also mention here. In parameter estimation, we will be interested in functions of the data that take on values in the parameter space, and these are then called point estimators, as I will define in a second. In confidence interval evaluation and hypothesis testing, one is also interested in what is called statistics. And statistics are just functions of the data that not necessarily take values in a parameter space, but in a real number space usually. So that's the difference, if in a way, in between the terms parameter estimate and statistics. So parameter estimate is a function of the data taking on values in parameter space, and a statistic is a function of the data that does usually not take on a value in parameter space, because then it would be called estimator. So that's kind of a little bit of an outlook of what will happen. What we will be concerned with for the next 3 weeks are point estimators. So point estimation, and here's a definition. So let the random variables x1 to xn be distributed according to probability distribution with PDF or PMFP theta. So n independent identically distributed observations of a parametric statistical model P with parameter space theta. Then a point estimator theta hat n for theta is a function of the random variables x1 to xn that takes on values in the parameter space, as I already mentioned. So we will denote point estimators with a head. You see here that I don't write out the full functional form. That it's a little bit tricky always. I mean, we've seen that previously, that we deal with transformation of random variables, and of course the functions themselves are defined on the values that these random variables can take on. But if you have if you apply your functions to realizations of random variables, then of course the outcome of your function becomes a random variable itself. So then sometimes one has to think about whether one actually is applying the function to random variables or to numbers. So instead of going to the details and subtleties, it's just defined here as a function of the random variables without specifying where these random variables live and so on, and denoted here just by theta hat. And we will often have this n here because this refers to the fact that there are n random variables. And at one point we will be interested in studying what happens if n is smaller or larger, or what happens for fixed n. So this n often then plays a role. Sometimes we omit it. I think it's not completely consistent in terms of the notation of the lecture. But when we need it, then of course it will be there. A point estimator is a single best guess of some quantity of interest, namely the parameter. It is a random variable because it's a function of random variables. The data are random variables, so the point estimator also has a distribution. If you sample different data, you get a different value for the point estimator. A value taken on by a point estimator is called a point estimate. So the estimator being the function, the estimate being the value that is taken on by the function. And of course, frequentist inference is, and specifically the qualitative, the qualitative theory of frequentist inference is concerned with the properties of point estimators, and this is what we will see next week and the week after when we talk about finite sample size and infinite sample size estimator properties. The question is how to get point estimators, and there are different ways you can get point estimators, of course, and actually it's not that important how you get your point estimators in the first place. What is more important is that your point estimators fulfill certain quality criteria. So you can, of course, you can come up with an estimator that takes on a constant value. So you can say, regardless now of the specific statistical model, I estimate the true but unknown parameter by 3, and you do that whatever happens, and very rarely you will be right. Most of the time you will be wrong, but it's a point estimator. The question is then not so much how you derived or where your point estimator is coming from, but how well this point estimator actually performs in the frequentist setting. And there are different ways, however, to derive sensible estimators, and for example maximum likelihood estimators that we will discuss are guaranteed to have some desirable properties. So if you use a maximum likelihood procedure to derive some estimator, then with the fact that these estimators are maximum likelihood estimator comes the fact that they have the properties of maximum likelihood estimators, which are in general good estimators. So it also makes sense to use certain procedures to derive estimators because they then guarantee certain behavior of estimators. And we will discuss here maximum likelihood estimation for the theoretical exercise session that we do, I guess, today at 2. I will present there also two other methods for deriving estimators, namely the methods of moments and the more general approach of M and Z estimators. So maximum likelihood estimation is not the only way to derive estimators. It's also not necessary that in a statistical model you always find a maximum likelihood estimator. Sometimes they might not even exist. But if you can identify a maximum likelihood estimator, as we will see later, you have certain guarantees on the behavior of these estimators. So the important point is more the qualitative behavior rather than the procedure to derive an estimator. Now, this whole thing in point estimation and studying the qualitative properties of a point estimator unfolds against the background of this frequentist sampling intuition. And in a way, I hope that this is clear to everyone already from undergraduate statistics. So maybe it's a little bit oversimplified what I present here next, but maybe it's also not, because this is really what you need to get clear about if you think about frequentist statistics. Bayesian statistics is different in this regard, but frequentist statistics works as follows. So you model some observed data by assuming that the data that you observed are realizations of a set of random variables x1 to xn that are distributed according to a certain distribution that you assume. And it's always important to realize that you observe data that somebody or you yourself acquired and which is saved somewhere and which sits somewhere, that you consider that one of the possible realizations of these n random variables. And there's also always a little bit of confusion. If you have n data points, each of these data points, so each of these numbers, is conceived as the realization of one random variable. Yeah, so these x1 to xn, they are not repeated samples or refer to different data sets. If you have 10 data points, you assume there are 10 random variables, and each data point is the realization of the corresponding random variable. And the difference between observations and random variables is usually then emphasized by using lowercase letters to denote realizations. So if you have real observed data as one of the realization of your n random variables, then you have n data points, and your actual observed data, you might give a little 1 or superscript with a little 1, but in any case you have one realization. Based on this one realization, so your 10 data points, your 10 numbers, you can compute a point estimator. Now let's assume that the point estimator that we're interested in here is an average, so you compute the average of your 10 data points. Now the fundamental idea of frequentist statistics is that while your observed data is one of the realizations of your random sample of your statistical parametric model, you could in principle, or at least the mathematical machinery allows you to sample more often from your model. So you could again take let's say 10 numbers from your model. Of course, in real life you only have one sample. Yeah, that's important to realize. Sorry, but the mathematical model states that there is a distribution, so in principle you could sample more often. And if you sample for a second time, then of course you can, also in this hypothetical sample, again compute an average and have another value for your point estimator. And of course you can do that multiple times in the theory of your statistical parametric model. And then you have as many values of your point estimator as you took samples from your n random variables. And the frequentist inference theory is then interested in the distributional properties of these estimators. These are the sampling distributions of estimators, or the frequentist distributions of estimators or statistics, and these are the distributions that your actually observed statistics or estimators are then compared against. Yeah, so these are hypothetical distributions in the sense that they are not observed. You don't get these distributions from observing many data sets and computing a histogram or something, but they are inherent in the theory. They are induced by the assumptions and by the core assumption that you conceive each observed data point as the realization of a random variable. So that's crucial. That's the frequentist sampling distribution. It's also crucial that you realize that your observed data set is one of the many realizations that your statistical parametric model allows for, and then you ask under certain assumptions about the model. For example, if there's actually no effect, how likely is it, or if a certain parameter is actually 0, how likely is it to see this observed data point? That's of course the logic then of p-values and hypothesis testing. And these sampling distributions, these frequentist distributions, they are then studied in frequentist inference in final sample estimator properties for fixed n, and in asymptotic estimator properties for n going to infinity. So this frequentist sampling intuition that underlies the study, the qualitative properties of estimators that we will see next week and the week after, as well as confidence intervals and hypothesis testing that really needs to, you really need to anchor this strongly in your understanding of statistics, otherwise it will always be confusing. Good. I think I want to continue. I thought briefly about taking a break, but I think we should just continue and get started with the maximum likelihood estimation for the next 15 minutes. So we now introduce what statistical models are. We also introduce the notion of a point estimator in a statistical model, namely a single best guess for the true but unknown parameter value. And now we are looking at one procedure of how to derive point estimators, and a procedure that, as we will see then when we discuss the asymptotic estimator properties, is also a method that gives you estimators with certain desirable properties, and that method is called maximum likelihood estimation. Now, maximum likelihood estimation rests on the maximization of the so-called likelihood function, and then usually in a practical setting the log likelihood function. And we start with some definitions here. So if we have a parametric statistical model P with PMF or PFP theta x, and we have a random sample of n random variables, then the likelihood function is defined as a function from parameter space to the non-negative numbers. The likelihood function allocates to each value in parameter space a value of the likelihood function, and the value that it assigns to the parameter space is the joint probability of observed or potentially observed data, and this joint probability, because it is assumed that the x1 to xn are independent and identically distributed, factorizes into the product of the marginal probabilities of each of the data points. Yeah. So this product here with respect to the probability mass or probability density function of each data points results from the fact that the random variables are assumed to be independent, and then the likelihood function does not state anything but that it allocates to each parameter the probability of observed data under a given model, of course, of observed data given this value of the parameter. Yeah, so crucial is here, of course, that the probability mass function PDF has a parameter, and this parameter is the value that is of concern here. The log likelihood function is just defined as the log of the likelihood function, and I think we will discuss some reasons why it's often better to use the log likelihood function, or easier mathematically. So the log likelihood function is also a function of the parameter, takes on values in the real numbers, and it allocates to each parameter value the log of the likelihood function. So again, the likelihood function just refers to the joint density or joint probability mass of the data, and there you can of course, and this is also something you should realize, if you have observed data, then it's clear what the data is, because that's your observed data. But of course, we also just learned that we, from the frequentist viewpoint, we can of course sample data repeatedly from the parametric statistical model. That means that also the value that the likelihood function takes on for a given value of the parameter is a random variable. So likelihood functions are actually random functions in the sense that the values that they take on for a given parameter value, of course, depends on the data realization. In a concrete context, when we do maximum likelihood estimation, we have observed data, we have one fixed data set, and then it's a fixed function of the parameter. But in the theoretical setting of a parametric statistical model, it's of course a random function, so it takes on different forms for different data realizations. It's crucial to, because that can of course is easy to confuse, so especially if you sometimes look at these very basic and usually quite bad introductions to Bayesian inference, where the likelihood is coming up, and then there's you always get this confusion between what is a likelihood and what is a probability, and of course a likelihood, these are just terms, and the crucial thing here is that the likelihood function, of course, it gives you the joint density of data, but the crucial thing is that the likelihood function is a function of the parameter and not a function of the data, because a joint density, a probability density function, is a function of the values of random variables. This is not what the likelihood function is, although it takes on the same values for the same data and the same parameters, but it's a function of the parameter. So the functional definition, so the domain and the range are crucial for the likelihood function. And because that is the case, the likelihood function usually does not integrate to 1 with respect to theta. There's absolutely no reason why it should. Of course, a probability density function and a joint probability density function over the random variables that this joint probability density function describes, this of course integrates to 1, but a likelihood function over its domain. But a likelihood function is a function of parameter space, and it's doesn't assign probabilities of parameters to parameters, but it assigns probability of data to parameters. Yeah, so this is crucial. So this this functional definition, that's really, if you yeah, this is what you need to. Today I'm lacking the word for what I actually want to say here. You need to really absorb, maybe that's one word. Now, based on the definition of the likelihood function, the maximum likelihood estimator is defined as a value of the parameter that maximizes the likelihood function over parameter space. And because the logarithm is a monotonic transform, the same value that maximizes the likelihood function also maximizes the log likelihood function. So if you maximize the log likelihood function, so you find a parameter value that maximizes the log likelihood function, you also found a parameter that maximizes the likelihood function, so you have a maximum likelihood estimator. So that's what's stated here. Because the logarithm is monotonically increasing, the maximum of the log likelihood function occurs at the same place, so the same parameter value, as does the maximum of the likelihood function. And this here, this could be deleted. Working with a log likelihood function is often easier, I don't, maybe there are not these reasons why it's easier. So one thing is that, as we will see later on, if you assume a factorization over the random variables constituting your sample, then of course if you apply the logarithm to that, you get to a sum, and sums are easier as then compared to products when you're trying to maximize things. Another reason is that you often, if you're dealing with specifically if you're dealing with distribution from the exponential family, you have exponentials in the parametric forms or in the functional forms of your probability density or probability mass function, and then you get away with the exponentials, as we will see for the Gaussian. Another reason is also that you stretch out small numbers, so the values between 0 and 1 to a bigger space. So if you have limited computer numerical resolution, then you are also a little bit more sensitive there. So there are good reasons to work with the log likelihood function, and the typical approach, just that you find in all books, is to work with the log likelihood function. Then constant contributions to likelihood functions are not do not make a difference. This is maybe we see that later, but of course the important thing is how the likelihood function or the log likelihood function changes as a function of the parameter. So that's so if you have additive constants, or if you multiply the whole thing by a number, that doesn't really make a difference. In the end, and this is what maybe the core message here, in the end, maximum likelihood estimation is a problem of function maximization. So in an applied setting, you will often use numerical optimization to do a maximum likelihood estimation, as we will also see in the second hour, and then also in one of the examples, or maybe two, I think, in the exercise. So the thing from my perspective, when we develop a new model and we want to do a maximum likelihood estimation, the crucial thing from my work is to write down the model, write down the log likelihood function, implement that, and then usually use some black box optimization method to maximize that function. Because otherwise I wouldn't do maximum likelihood estimation and probabilistic modeling, but I would do numerical optimization. So this is where my boundary lies. Although of course sometimes we also look a little bit into the optimization methods themselves and propose other ones that are around. But in the end, it's a question of function maximization. And now, before we look at some examples for maximum likelihood estimation in a second hour, you can view, and this is something that I like to do and that I always like to do in math, is to kind of see these as a kind of standardized procedure. So if you want to do a maximum likelihood estimation, then the first thing that you need to do is formulate the log likelihood function, because if you don't write down the log likelihood function for estimating a parameter, you cannot maximize it. Then at least in analytical approaches, so these typical textbooks examples and the simple cases that we will look at here, is that you maximize by looking at the derivative and setting to 0, as you are all familiar from basic analytical function maximization from school already. And then once you set the derivative to 0, because you know that it's the necessary condition for a function to have a maximum or minimum, if the derivative is 0, that was not nicely formulated, but you know what I mean. Then once you solve for a critical point where you potentially have a maximum, then you can sometimes verify that. We will actually not look at verification here, so looking whether the second derivative or the Hessian matrix is positive, definite, or positive. Positive, negative, positive, negative, sorry. This is usually not done because most of these functions are concave, so that it's actually problems of convex minimization, and then for convex functions you know that they have a definite minimum. So usually what you find in statistical textbooks is just computing the derivative, setting to 0, and solving. And as I now already mentioned, there are two ways of maximum likelihood estimation. One is the analytical approach that you find in the classical examples and small examples that we will also look at here, and then the more applied and actually in novel models that you of course develop as data scientists, the more common approach is to use some numerical means for maximization. Yeah. Good. So I think this was then introduction to kind of statistical models, frequentist inference, and maximum likelihood estimation. And now I think it's definitely time to look at some examples for that and show you maximum likelihood estimation in practice. If there are questions, please hold them until the beginning of the next hour. So I will ask about questions at 8:30, but now I think it's time for a break, and we will continue at 8:30 looking at examples of maximum likelihood estimation. Now let's look into some examples for maximum likelihood estimation. And starting with some analytical examples. So there are actually two examples that will pop up throughout our study of estimator properties, and also then Bayesian inference, and these are these very basic examples of Bernoulli random samples and univariate Gaussian random samples, and we will now I show you how to derive the maximum likelihood estimators, but we will then again also study these estimators and then also look at Bayesian alternatives for that. So these examples are quite fundamental, so yeah, absorb them. That's what I suggest. Okay, so the first example is estimating the parameter of a Bernoulli distribution statistical model. So assume that you have n random variables distributed IID according to a Bernoulli distribution, and the aim is to estimate the value of the parameter mu. To do so, as I described previously in before the break, you can in maximum likelihood estimation you can follow a procedure, and the first thing there would be to formulate the log likelihood function. There it's usually helpful to start with the likelihood function and then taking the logarithm, because the log likelihood function is the log of the likelihood function, and the likelihood function you just get from the functional definition of the respective probability density or probability mass function. Here the probability mass function, which you see here, so mu to the power of x times 1 minus mu to the power of 1 minus x for a single Bernoulli random variable. in the case of n random variables all distributed IID according to the Bernoulli distribution, mu to the power of xi times 1 minus mu to the power of 1 minus xi is the probability mass function of the ith, the marginal probability mass function of the ith random variable, and then because the assumption is that they are independent, the joint probability mass of all random variables is given by the product of these marginal probability masses. And then the likelihood function allocates the joint probability mass of all n random variables to a specific value of the parameter mu. Yeah, so mu is here the input argument of the likelihood function, and the output argument is just the joint probability mass of the random variables x1 to xn. So that's the likelihood function. So this is always the same. If you assume independence, you just write down the product of the probability mass function or the probability density function of the random variables that you consider. So you write out the factorized joint. Sometimes, like here, you can then simplify this a little bit. So here we can write this as mu to the power of the sum of the xi and 1 minus mu to the power of n minus the sum of the xi, which is just derives from the properties of potentiation. Then the next step in writing down the log likelihood function is to take the logarithm. So this is then usually, so you just take the logarithm of the factorized joint density, and there then often things get a little bit simpler, because often you have these powers which then turn into products, like here. So you have the logarithm of mu times the sum of the xi plus the logarithm of 1 minus mu times n minus the sum of the xi. And if we later then in a second look at the Gaussian, then we would actually do away with exponents. Then the next thing is to maximize the log likelihood function. Sometimes actually when you do things numerically, you will actually, because numerical packages usually, and the entire field of nonlinear optimization is of course not concerned with maximization but with minimization, and then you need to minimize the negative log likelihood function. But here we just continue with maximization. So we compute the derivative of the log likelihood function with respect to its parameters and set to 0, and this then we actually want some brackets. This is what I just realized here. It's always nice that I only see the typos in show. So let's so that's fine. I just want to put brackets around expression. And then of course from the linearity of the derivative you need the derivatives of each of these terms, and then you follow the standard rules of calculus. So the derivative of the logarithm is 1 over this, products remain there, derivative of the logarithm is 1 over this, and then you already if you set the derivative then to 0, you already have what is known as the maximum likelihood equation. So this term also comes up in maximum likelihood estimation quite often. So the likelihood equation or maximum likelihood equations, these are just the derivatives of the log likelihood function set to 0. And because these if sometimes these are multiple equations, they then define a system of equations, or in this case a single equation that you need to solve to identify estimate. And of course you need to solve it for the potential parameter value, which is what we do in the third step here. So yeah, basically by taking our bracketing this and multiplying it, pre-multiplying it, we then get to the fact that our value that solves this equation is actually 1 over n times the sum of the xi, which is of course the average of the xi. So remember that the xi in Bernoulli trials or Bernoulli random variables are all zeros or ones. So for example, if you have 10 Bernoulli random variables and you have like a mu parameter, which is the probability for each random variable to take on the value 1, and your mu parameter is, for example, 0.7, then it might be the case that you observe, if your sample is nice, you observe 6 ones and 4 zeros, and then you have as average 0.6, and then you're not too much off from your true but unknown value, which was 0.7, and you estimate it with 0.6. So here the average is a candidate from this maximum likelihood estimator for mu, and then one can check whether this actually maximizes the log likelihood function, which is something that that I don't include here. And then I always write this can be consolidated, so our maximum likelihood estimator is the average of the xi. And this is then often the case that it's kind of the maximum likelihood approaches, they yield sensible estimators. So of course you need to historically invert this procedure. Of course people computed averages long before maximum likelihood estimation was proposed as a fundamental principle. But nevertheless it turns out that maximum likelihood estimators often take or are often evaluated or correspond to sample averages. Second example, Gaussian random variables, where your parameter is now a parameter vector comprising mu and sigma square, and again the approach is the same. So you first formulate the log likelihood function by considering the likelihood being the product of your marginal individual probability density functions, which is here of course the univariate Gaussian, which then can be simplified a little bit using the product and some properties of the exponential function, and just using the roots of potentiation, and then taking the logarithm in this case then of course simplifies things further. So powers get turned into products and exponentials go away. So the log likelihood function then looking a little bit nicer or easier to treat. Anyway, but now this log likelihood function is a function of two values, namely the expectation parameter and the variance parameter, and then one way to conceive the whole thing is that one sets the gradient of the log likelihood function to 0, so one computes the partial derivative with respect to each parameter. So here I compute, or another way to do it, and this is actually a little bit more of what I actually wrote here, is to conceive the log likelihood function as a function of one of the parameters at the time. So here I just consider it for fixed sigma square, consider it a function of mu, and compute the derivative with respect to mu, and then of course because mu is here in the square, you get away with the square, you get away with the negative, so the minus sign, because you have this minus sign here, and you need to use the chain rule, and then you get to 1 over sigma square corresponding to the, times this sum. And the same thing for fixed mu, then computing the derivative with respect to sigma square, where the sigma square shows up here once in this logarithm term and once here in this factor. And here, I mean, with the Gaussian, with univariate Gaussian, you just need to realize, or you compute the derivative with respect to sigma square, and then if you need to multiply sigma square with sigma square, you get sigma to the power of 4 here. And then setting these to 0, you already have the likelihood, maximum likelihood equations. Here at this point I remove this sigma square because this cannot be 0. Because it needs to be larger than 0. So you have the maximum likelihood equations, which then need to be solved, and solving the first one yields again the sample average as a candidate maximum likelihood estimator for mu. And then the problem here with maximum likelihood estimation in the Gaussian is that the maximum likelihood equation for sigma, for the estimator of sigma square, also is dependent on the true but unknown expectation parameter, and there we cannot do something like here where we know that sigma square is always larger than 0. So the solution that is commonly used then here, or that is used, is to substitute the true but unknown value with the estimate, which leads to certain problems actually with the maximum likelihood estimator for the variance parameter of the Gaussian. It's not the best estimator that you can get. It has the properties of maximum likelihood estimators, but we will see fairly early on that it's, for example, biased. So that's something that we will discuss next week, and you can have better estimates for the variance parameter of a Gaussian, which has to do with the fact that we here substitute the estimate for mu. In any case, what we get for the maximum likelihood estimator candidate for sigma square is that we get the average sum of error squares. So we compute for each sample value the difference to the estimated expectation parameter, square all of those, and divide by the number of data points. And both of them from this are of course established as candidate values for the maximum likelihood estimator, but they can be consolidated. So the maximum likelihood estimators for the univariate Gaussian are the sample average 1 over n, the sum of the xi, and the sum of deviation squares of the sample values from the maximum likelihood estimator divided by n. And if you already remember something like sample mean and sample variance, you might remember that the sample variance uses an n minus uses the denominator n minus 1 here, and we will get back into that business when we compare estimators. But the maximum likelihood estimators for the parameters of the univariate Gaussian are just the sample mean, or the average of the data points, and the sum of error squares, residual sum of squares, I think that's the official term, residual sum of squares divided by n. So there are many more examples for this. Actually, in the theoretical exercise session, I will show you one more example that involves estimating the parameter of a uniform distribution on a given interval 0 to theta. But what if you now study maximum likelihood estimation in different models, what you can always look out for, and to clarify how these things come about, is to where does the log likelihood function come from? Again, product of the marginal densities or marginal mass functions of the samples, taking the logarithm, then computing the derivative, or computing the gradient, meaning the partial derivative with respect to all elements of the parameter vector, and then writing down the maximum likelihood equations, that is setting these derivatives or the gradient to 0, and solving for the parameter values. These are then the maximum likelihood estimators. And you will find many more examples than the ones that I presented here, but these are the most common that we will use throughout the lecture. Now, this is fine to study statistics and getting into maximum likelihood estimation. However, in real life, then specifically if you create novel statistical parametric models that are a little bit more complex, where you not necessarily want to do or even can do all these things by hand, you often want to use numerical approaches for maximum likelihood estimation, which you can of course do in a black box manner simply by writing down the log likelihood function, then maybe writing down the negative of the log likelihood function and minimizing this. But there also exists certain things that have been established in this setting for longer that may or may not be better than what you're doing with your latest optimization routine. And this is what I want to talk here a little bit about, namely Fisher scoring. So the key term that or what this whole last section here of this in today's lecture will establish is Fisher scoring, which is one way to do numerical maximum likelihood estimation. So as I previously said a couple of times, is that numerical maximum likelihood estimation rests on first formulating and then also, if you run it on computer, implementing the log likelihood function. Is the same thing as negative log likelihood minimization, and is a problem in non-numerical optimization. And of course you can do this with many methods. So there are things like deterministic and stochastic optimization. You can use constrained or unconstrained optimization, local or global optimization. Of course you usually want to do global optimization, but often these algorithms actually don't do that. And you can do gradient-based optimization or gradient-free optimization. It's essentially a problem in nonlinear optimization, and there are good books on nonlinear optimization. For example, this book by Notstetter and Wright. I think that's really nice. Like I also said, we consider a specific method which is called Fisher scoring, and that's actually a variant of the Newton-Raphson method. Now, to introduce that, I will first tell you what the Newton-Raphson method is, and then tell you what Fisher scoring is. It's something that, Fisher scoring you find in statistical papers. I don't know, certain models in certain software packages these days might, of course, still implement might implement Fisher scoring, but of course there are also alternatives. So first, if you are not that familiar with numerical optimization, then I'm now introducing kind of a first method to do numerical optimization, which is Newton-Raphson. Of course, numerical optimization is not only applicable in the context of maximum likelihood optimization or negative log likelihood minimization, but it's optimization and numerical optimization refers to the general problem of finding extrema of functions, usually real valued functions, and in the simplest case the univariate, and in more general cases and actually more common cases multivariate real valued function. So functions that take on that have as arguments scalar numbers or vectors, but then always as their outcome value, as the value that they take on, have a scalar. So these are, of course, if you are also doing machine learning, these are in sometimes they're also called loss or cost functions, if they are the functions that are minimized in a certain learning problem. The univariate Newton-Raphson method is now one method to do numerical optimization, and most of these methods rests on the idea that at a maximum the derivative of the function that you're trying to maximize takes on the value 0. And then most optimization methods, and hence also the Newton-Raphson method, are of course iterative procedures. So you start with an initial guess, and then you form iterants according to a certain rule. So you create a sequence of parameter estimates that hopefully get better as the algorithm continues. And here the idea is to approximate the point of a maximum by using a first Taylor approximation of the derivative of the function that you're interested in. Alternatively, you can view this as a second order Taylor approximation to the function itself, which I think will be it's already stated here, which we will also see. And the crucial thing then, of course, to realize for a maximum likelihood estimation is that the function that you are trying to maximize is a log likelihood function. Now, the basic motivation for the Newton-Raphson method is to figure out a 0 of the derivative, so figuring out whether the derivative of the function that you're trying to maximize has a 0, so where it's 0, and this is done by approximating the derivative of the function that you're trying to maximize by a first order Taylor approximation. And the first order Taylor approximation then takes the form, so the approximation here is denoted by this tilde. So you're trying to approximate the derivative of f by a first order Taylor approximation here denoted by tilde f, and this first order Taylor approximation is given by the derivative of f at theta k plus the second derivative at theta k times theta minus theta k. So don't get confused here. It's a first order Taylor approximation, so you have the function and the first derivative of the function and the first order deviation here. There are only this derivative and the second derivative only show up because you're approximating already the derivative. Yeah, it looks a little bit, so if you, of course, you know what a first order Taylor approximation is, and usually there you don't have the second derivative, but you have it here because the function that you're trying to approximating by a first order Taylor approximation is already a derivative, and hence because the derivative of the derivative is the second derivative, you here see the second derivative. Now, based on this approximation, you try then to identify a 0. So the idea is to set this Taylor approximation to 0, meaning setting this expression here to 0, and then solving for the value of interest. So the this value here where the approximation to the derivative has a 0, that's what's happening here. So first the this term is taken to the other side, then it's divided by the second derivative here, and then the minus theta k is taken to the other side, and then you have a solution here, theta tilde, that that describes where the approximation to your function of interest has a 0, and this you can compute by taking theta k and subtracting from it the function value at theta k divided by the derivative of your function of interest, which is the derivative of f, at theta k. So you have an update rule for theta k if you do that repeatedly. So the univariate Newton-Raphson algorithm then proceeds by defining a starting point if the derivative of the function that you're looking at that starting point is already 0, then you stop and you found a 0. If not, you go to the iterations and you compute theta k plus 1 by theta k minus the derivative of the function that you're trying to maximize divided by the second derivative of the function that you're trying to maximize, and then you stop if you found a 0 of the derivative. So here's an example. So the gray, or a visualization, the gray curve is supposed to represent the derivative of the function that you're trying to maximize. Here is the 0, so at this location your function then can have a maximum, and the way this works is that you use a first order Taylor approximation to this derivative, and your first order Taylor approximation is of course a line, and here you have the first order derivative, and sorry, here you have the first order Taylor approximation. You start at theta k and you go with your theta k plus 1, you go to the place where your first order Taylor approximation has a 0. So this is what was evaluated here, and of course then when you do that you are not at the 0 of the function that you're actually trying to minimize here, f prime, but you are at a new location and you again try to you again first order Taylor approximated and go to a 0 of your first order Taylor approximation, which is then here at theta k plus 2, and if you now think you continue doing that, then at one point you would end up here. So this of course works because you're because the gray function, so the f prime theta that I visualize here, actually has this specific form. One can motivate the whole thing also from a second order Taylor approximation, so basically starting or with the function itself and saying, okay, we want to approximate it with a second order Taylor approximation, and then looking at the derivative, because again we try to find a 0 of the derivative, which is then of course the location of a candidate location for a maximum. Now we approximate the function of interest with a second order Taylor approximation, meaning that we need to look for a 0 of our second order Taylor approximation, and then yeah, you can have a look at that. You get to the same update rule, so it's a different motivation. The tricky thing that can be a little bit confusing here all the time is that you're looking for a 0 of the derivative of the function, yeah, because you're trying to find a location where the necessary condition for a maximum, minimum, or saddle point is fulfilled. Now, commonly you not only have a single parameter, but you have multiple parameters, and there is the generalization of the univariate Newton-Raphson method known as the multivariate Newton-Raphson method. So here you're trying to minimize a function of multiple values that takes on real values, and the update rule for the multivariate Newton-Raphson method you basically get by generalizing what you have in the univariate Newton-Raphson case to the appropriate multivariate calculus quantities. So the derivative is replaced by the gradient, and the second derivative is replaced by the Hessian, and of course you divide by the second derivative at the location theta k, so you look at the inverse of the Hessian. So that's basically how you get from the univariate Newton-Raphson method to the multivariate Newton-Raphson method. So replacing the first derivative by the gradient, which is actually not the best thing that you can do. Actually, it would be so the the analog of the first derivative is the Jacobian and not the gradient, but it works out here fine. And replacing the second derivative, the inverse of the second derivative, or the reciprocal of the second derivative by the inverse of the Hessian, which is just the matrix of all the second order derivatives, as I guess you all know. So the multivariate Newton-Raphson method then rests on this update rule. So your parameter vector at iteration k plus 1 is given by your parameter vector at iteration k minus the inverse of the Hessian evaluated at theta k multiplied with the gradient of your function at location theta k. And then you always check whether the gradient is 0, and if it is, you stop. If the gradient is not 0, so your first derivative, then you don't stop. Yeah. And why did I introduce all of this? Because Fisher scoring is the application of the Newton-Raphson method to log likelihood functions, and is also in a way a simplification of the Newton-Raphson method in this specific setting, because instead of looking at the Hessian at the location theta k, which can be quite computationally demanding, it looks at its expectation. Now, what is a multivariate Fisher scoring algorithm? So we are in the scenario of a parametric statistical model. We have its log likelihood function, and a multivariate Fisher scoring algorithm is then just the multivariate Newton-Raphson method applied to the log likelihood function. So the objective function f in the Newton-Raphson method is replaced by the log likelihood function. The gradient is replaced by what is known as the scoring vector or the score vector, but that's not really a replacement, it's just a new name. So instead of calling this the gradient of the log likelihood function, you call it the score vector. And the Hessian matrix of the objective function is replaced by the expected Fisher information, which is the negative expectation of the second derivative of the log likelihood function. And in this case, the second derivative is of course the Hessian, so it's the expected Hessian. Now the terms score function, score vector, and expected Fisher information, they will come up big time next week. So here it's kind of a little bit jumping ahead. We will look into score vectors and Fisher information in quite some detail next week. And they play quite a role in studying the estimator properties. Here they are just kind of introduced a little bit out of the blue, but are inherent to this Fisher scoring method. So the basic idea, that's what I just said, the basic idea of a Fisher scoring algorithm is to replace the gradient of the log likelihood function by the score vector, but that's not a replacement, it's just a different name, and replacing the Hessian by the expected Hessian, the negative of the expected Hessian, which is known as the expected Fisher matrix. And the question is, where is the expectation coming in? Well, this is the log likelihood function, which of course depends on the data. So you might often have data variables in there, and if you can evaluate the expectation, then you get rid of data dependencies, and often you even get rid of parameter dependencies, and then your Hessian matrices are just constants. We will actually see an example for that today in the exercise session, where the expected Fisher information matrix takes a fairly simple form, namely in the case of simple linear regression, and then this actually simplifies the multivariate Newton-Raphson method. So yeah, This was kind of a introduction to Fisher scoring, which is something, so that's the key thing here of this last bit. So the key topic of this last bit is Fisher scoring, and the question, what is Fisher scoring? And Fisher scoring is, as I said, in the application of the Newton-Raphson method to multivariate log likelihood function, and Fisher scoring is something that you find in the context of statistics, and so it's good that you know what it is. So one example for numerical maximum likelihood estimation, of course, there are different ways, as also laid out here, for maximizing a log likelihood function. Good, so this is what I wanted to do in terms of maximum likelihood estimation. In the exercise session, then we will, and I think we should do it also in this order, we will first do the programming exercises. Where are we? There. So these will be 3 presentations on numerical estimation of Bernoulli random variable parameters, the distribution of these parameters, and then actually looking at a concrete Fisher scoring algorithm for maximum likelihood estimation. So these looking a little bit at the numerics and training a little bit to develop maximum likelihood procedures at the implementational level, which is of course the much more common practical aspect. So we will do that at 1 and should be done by 1:45, and then in the last hour of today's session I will show you in these exercises first yet another maximum likelihood estimator where it's a little bit different than to the procedure that I described, and then show you also 2 alternative methods for deriving estimators, because there is not only maximum likelihood estimation, there's also a method of moment estimation, and there are M and Z estimators, and these things you might also encounter. Okay, yeah, so in summary, let's go to a summary slide there. Today we introduced the basic foundations of frequentist inference. Of course, this rests and all these things that we learned about before, probability distribution, probability mass function, probability density functions, expectations, and so on. All these things will feature heavily in the coming weeks. Then we looked at maximum likelihood estimation as a general procedure to derive estimators. Why it's a good procedure? I mean, it's intuitive to use. I actually haven't said that, but it's intuitive to use the parameter that under which the data have the highest probability of occurring. Maybe I should have said that earlier, but that's of course the basic intuition. But the real benefit of maximum likelihood estimation, besides this intuition, that it's a good idea to take that parameter value under which the observed data have the highest probability to occur. The real value, I think, only gets clear once we looked into asymptotic estimator properties, and then we looked at a couple of examples in the analytical setting, and I showed you Fisher scoring as one of the numerical approaches for maximum likelihood estimation. Good. So from my side, that's it. At 1 we then start with the presentations. Good. So the last bit of this exercise session, which I'm taking over, is essentially to go a little bit beyond what we did in the lecture, to show you that there are other things and other theoretical aspects to point estimation that one can delve into and learn about. And the first exercise is kind of showing that my 3-step procedure for maximum likelihood estimation, so writing down the log likelihood function, computing its derivative, saying to 0, and then solving, that works in most cases. Sometimes it looks a little bit, or the whole approach needs to be a little bit different, and that's in this first exercise. And then I want to show you briefly other methods to derive estimators beyond just making them up, which is of course also a way if one then studies the qualitative properties. So based on intuition, you can of course say, let's estimate things like that, and let's see whether that's something sensible. But there are also other procedures, and these are methods of moments in MNZ estimators. But let's first look at another example for maximum likelihood estimation, and here it's about estimating the parameter of a continuous uniform distribution. So we assume that we have n random variables which are distributed according to a continuous uniform distribution, which is parameterized by its upper boundary. So it's a continuous uniform distribution on the interval 0 to theta, and theta being larger than 0. And then of course the probability for each of these random variables to take on a value between 0 and theta is 1 over theta, so that the whole interval with positive probability mass integrates to 1, and it's of course 0 for the probability for the random variable to take on values outside this interval from 0 to theta. So for the values of the random variable to be, or for values that are larger or equal to 0 and smaller or equal to theta, the likelihood function is just 1 over theta n, because that's the product of 1 over theta, and each marginal random variable has PDF 1 over theta on the interval in which the random variable takes on values. And here then it's not immediately clear how now to go about that, and this is the de Groot and Chervish approach. So first it must hold that because this is the likelihood function for samples that take on values between 0 and theta, it must hold that because the maximum value that the maximum likelihood estimator can take is obviously theta, and all samples are smaller or equal to theta, must hold that the maximum likelihood estimator is larger or equal to xi for all I, and it must maximize the likelihood function. Now, so there are two constraints. First of all, the maximum likelihood estimator must be larger or equal to the data points for all I to n, and the second one is that it maximizes the the likelihood function. And this essentially results from the fact that this PDF takes on non-zero values only on the interval 0 to theta. Now the likelihood function is a decreasing function in theta, so it's 1 over theta n. So we are thus interested in the smallest value of theta, such that theta is larger or equal to 1 of the xi. Is such that theta is larger or equal than xi for all I to n. And this maximum, this value, so the smallest value of theta, but theta being larger or equal to 1 of the xi, all of them, but then also 1, is the maximum of the xi. Hence our maximum likelihood estimate for this parameter is the maximum of the sample values. This is kind of intuitive, so if you think you have data from a uniform distribution on some interval, and then of course if you have some value that is the maximum of that, there's no reason to believe that the theta, the true but unknown theta, is smaller than that, but yeah, it's also not completely trivial, I find, to think about this estimation from the perspective of maximum likelihood estimation, but it works based on these constraints here, and that you have that the that the likelihood function is a decreasing function in theta, so we try to maximize it by finding the smallest value such that these constraints are satisfied, and then we end up with the maximum of the data. So the maximum likelihood estimator for a continuous uniform distribution on the interval 0 to theta is the maximum of the observed data. So that's kind of a weirdish maximum likelihood application. So now I want to leave maximum likelihood estimation behind and show you two other approaches for deriving estimators in statistical models. So we will essentially only be concerned with maximum likelihood estimators for the remainder of frequentist inference, or mainly focus on them, and not discuss many more examples for moment estimators or MNZ estimators, but I at least want to have mentioned them. So first thing, method of moments estimation, which is quite a old school approach actually. So let P be a parametric statistical model with PMF or PDF P theta, and let x1 to xn be a random sample. And now assume that we consider k moments of x, where I think we didn't formally introduce the notion of moment because we don't do that much with it, or anything actually. So what we actually have seen is the first moment, which is the expectation, and we've seen the second central moment, which is the variance. In general, the moment of a random variable is defined as the or the jth moment of a random variable is defined as the expectation of the jth power of the random variable. So for some k, and k will be 2 in the example that I show you, we just take or we can evaluate the expectation of the jth power of the random variable. So that's our moment, and on the other hand, we consider the jth sample moment of our random variables, which corresponds to the average of the random variable values to the power of j. So again, if we take k being 2, then we have the first sample moment, which is just the average, and the second sample moment, which is just the average of the squares of our values. The methods of moments estimation then aims to match the sample moments with the random variable moments, or the actual moments, and chooses an estimator for theta such that the sample moments equal the true moments, or the random variable moments. So the idea is, in simplest terms, the idea is you take an estimator such that the mean of your sample corresponds to the expectation of each of the marginals. And in addition, with further constraints, you take an estimator such that the average of the squares of your sample corresponds to the second moment, so the expectation of the squares of the random variables. And you can, of course, do that to arbitrary order. So in a way, you try to match some basic statistics. I think, and this I didn't include this here, but I'm fairly confident that, of course, by matching the first and second moments, I guess you also match the, but I'm not completely sure, you match the second order central moment, so you match the mean and the variance with your sample mean and your sample variance. But we are just, I just wrote it down for moments, so I'm not completely certain there. That's kind of a simple idea. So you have this analytical expectation of a random variable or all of these random variables, and you have this empirical average, and you try to match them. And if you match them, you then think that, or you use this as estimates. This, however, often results in moment estimators that are not optimal. Actually, for the Gaussian, it's actually as optimal or suboptimal as maximum likelihood estimators, as we will see in a second. It's still around, so there is something called the Satterthwaite approximation. I think it comes up in repeated measures ANOVA, for example. It has to do with the squares of random variable. I can't really tell you more details at this point, but it's something that plays a role in day-to-day statistics, and this is based on the method of moments estimations. It's an old concept, and this was actually, so you might or might not know that Fisher in the early 20th century popularized maximum likelihood estimation, although maximum likelihood estimation was also used centuries earlier. But before, maximum likelihood estimation became quite popular, and then of course was also supported by asymptotic statistics results. The methods of moments estimation was around. Actually, I also no, let's not go into that. That's something different story for a different time. So that's the method of moments estimation, and here's an example to make this a little bit clear how this then works in practice. So we're trying to derive the methods of moments estimator for the univariate Gaussian parameter. So we assume we have a random sample with parameters mu and sigma square. And then if we want to use the methods of moments, of course we need to decide on how many moments we want to match, and here I decided for 2. And then of course our parameter here is the expectation and the variance parameter. And then the first thing that we need for the methods of moments to work is of course evaluate the moments of the random variable, so the random variable of interest here is a univariate Gaussian random variable, and the first moment as a function of the parameter here is of course the expectation of a univariate Gaussian, which is just mu, and it's a function of the parameter in the sense that it takes the first component of the parameter, and the second moment is the expectation of the square of the random variable, which you can of course evaluate fairly straightforwardly from the variance translation theorem, which says that the variance is given by the expectation of the squares of the random variable minus the squared expectation. And if you put the expectation, or you solve this for the expectation of the square of the random variable, then you just get, because the expectation and the variance of the Gaussian are of course mu and sigma square, you get that the second moment of a Gaussian random variable is mu square plus sigma square. Now the simultaneous equations of interest for the methods of moments estimations, which are like the log likelihood or likelihood equations in maximum likelihood estimation, then correspond to equating the sample moments. Did I call them sample moments? Yeah, the sample moments. So the average of the first order random variables and the average of the squared random variables to these moments, which are functions of the parameters, and then to call the solutions for these parameters the methods of moments estimators. And this is then the set of equations. So the sample mean is set equal to the first moment, and the square of the so the average of the squares of the random variable is set equal to the squared first moment plus the variance, which is of course the second moment. And then these need to be solved. Of course the solution is here already. So the method of moments estimator for mu is just the sample average, and here we need to put it's very simple, of course, put the mu square mm on the other side, so that we then get for the methods of moments variance parameter estimate, get that we have the average of the squared random variables minus the square of the average, which, and this is something which I don't know, it's something that one can show. It's actually popping up multiple times. I don't think I have proof of that at this point in the lecture already. This thing here, so the sum of the squared, the average of the squared random variables minus the square of the averages, can be reformulated as as 1 over n the sum of squared deviations, and this is of course also the maximum likelihood estimator. So the method of moments estimators for mu and sigma square in the case of the Gaussian correspond to what we've seen this morning, to the maximum likelihood estimators. And like the maximum likelihood estimator, the method of moment estimator for the variance parameter is not bias free, which is a term that we will only present discuss next time. But this is the logic here. So obviously we didn't define a likelihood function or log likelihood function and minimize something, but we followed these steps of setting up a set of equations such that the sample averages that we have match the moments, and then solve for the parameters that make up these moments, and call these the methods of moments estimators. Yeah. So here you are of course trying to, with your estimates, just try to hit the true expectation and try to hit the true higher order moments. So that's one example for methods of moments estimation. Any question regarding methods of moments estimation? I read somewhere that this is becoming more popular again as an initialization method for certain numerical algorithms, but I don't remember the details. So in the end, it's kind of 19th century estimation, whereas maximum likelihood is kind of 20th century estimation. Now, so methods of moments estimation is kind of predating maximum likelihood estimation, but there's also of course additional developments after maximum likelihood estimation, and these are so-called M or Z estimators, and that's the last thing that I then want to show you today. So you can view, and this is my current understanding of M and Z estimators, can view them as generalized maximum likelihood estimators, where you allow for other functions than the log likelihood function, because it may be helpful. And M and Z estimators have a role in robust statistics, where you want outliers to don't have that much an effect, and by using functions, the respective function in a specific way, you can then alleviate the effect of outliers. That's kind of a motivation. So here a definition. So again, we start with a parametric statistical model with a PDF p theta and a random sample, and then we call theta hat an M estimator if it maximizes a function of the following form. It's a function from parameter space to the real numbers, so very inspired, of course, by log likelihood or likelihood functions. And then here this function of theta is given by the average of a set of functions of each random variable. So we have 1 over n, so that's the number of variables, and we have the sum of functions of xi. And of course, if you think about log likelihood, there you always have the log applied to the product, so you always get to this sum, and inside the sum you have your random variables. So essentially it's just saying, rather than putting what the log likelihood function would tell us to put here, we put maybe something advanced there. But I will show you on the next slide that of course maximum likelihood estimation is a specific case of M estimation. Now this can even be taken a step further because you remember that in log likelihood estimation, the next thing that you maximum likelihood estimation, the next thing after formulating the log likelihood function would be to evaluate its derivative or gradient and setting to 0. So instead of talking about maximizing this function, you can also think about minimizing. So setting to 0 essentially, minimize an absolute value here, minimizing a function psi n, which is also a function from parameter space, and is evaluated for theta also as an average of these small psi functions of the data. And here the intuition is that these are actually the derivatives of the functions that you trying to maximize. So this is very much inspired by setting the derivative of the log likelihood function to 0, which it in general actually of course refers to a gradient. So yeah, so this is why we here have a k-dimensional function psi theta, sorry, and this is somehow wrong. Nay, this is, sorry, here this should be k-dimensional. Because you're trying to minimize a gradient if theta is multidimensional. So they are generalized maximum likelihood estimators, as I will show you later. This M theta are not necessarily likelihood or log likelihood functions and log likelihood function derivatives. And M and Z estimators, they actually post-date in a way maximum likelihood estimation and play a role, as I said already, in robust statistics. So here in this example, I just want to show you that maximum likelihood estimators are in fact special M or Z estimators. So assume that we have a parametric statistical model and now define this function here, one of these functions here, M theta, as the log of the density of X. Then the M estimator, which maximizes this function 1 over m, the sum of the log of each of the random variables, is of course the maximum likelihood estimator, because that's essentially this is, sum term here is just the log of the product of the densities, which is just what maximum likelihood estimation wants to do, and then it's here divided by n, but of course this doesn't change where the location of the maximum is. So the m, if you set this m theta function in an m estimator to be the log of the density that you're interested in, then you are back at the maximum likelihood estimator. And here it's the correct way. If you define psi theta to be the gradient of the log of the density, so this vector of partial derivative of the log of the density, then minimizing this big psi function here, which just corresponds to the sum of the gradients over your samples, corresponds of course to finding a zero of the gradient of your log likelihood function. So in this sense, M and Z, maximum likelihood estimators are special M and Z estimators. Of course, M and Z estimators only become really interesting if you don't use maximum likelihood estimators, because only then these functions can actually do something beyond log likelihood function. But this is also where my current knowledge of statistics ends, so I never really studied M and Z estimators so far. Good, but what I wanted to emphasize here is that maximum likelihood is not the end of the world. In statistics there are more things, there are older things, and there are newer things. In the end, where the estimators that you use for parameter estimation, point parameter estimation in statistical parametric models doesn't really matter. What is more important is that they are doing a good job, so that they are in some way reasonable estimators, because to come up with an estimator is easy. You can always estimate a parameter with a constant, but that's most likely then wrong, and the question is, what are quality criteria that one wants estimators to fulfill, and how do different estimators perform? So for example, how do maximum likelihood estimators perform in general? And this will be the topic then of next week and the week after. Good, so I'm happy. That was everything that I wanted to let you know. Are there any questions? Okay, then we stop here, and next week look at finite sample estimator properties, and start our study of how good estimators actually perform, what criteria are, and which estimators perform according to which criteria well or not so well. Okay, then see you next week. Bye bye.